inshallah, we will discuss a new topic in our course, which is magnetic circuits. Actually, magnetic circuits يعني considered very important in the electrical engineering because it's used in a lot of applications. For instance, you know your mobile phone include part of inductance or transformer. Also, any kind of motor includes some coils, and these coils also are based on magnetic circuits. In any kind of application in our life, you will find a lot of magnetic circuits. In solenoids, you have magnetic circuits. In relays, you have magnetic circuits. So we need to understand the component of magnetic circuits, what are the parameters of the magnetic circuit, and the applications as we discussed. So these are the objectives of the topics of magnetic circuits. So firstly, as we described, electrical machines have magnetic circuits in terms of stator and rotor cores and the coils. Transformers have magnetic circuits. Why we need magnetic circuit in these applications? Actually, magnetic circuit is very important in transferring power and also converting power from shape to another shape. For instance, for converting mechanical power to electrical power or electrical to mechanical, we need magnetic circuit in order to transmit the flux between two different cores. The same also for electrical transformers. Electrical transformers are used to transfer power by stepping up volt, stepping up or stepping down the volt. Okay, used in instrumentation transformers to measure voltage and current. So all of these can work only by the idea of power transfer between two coils. And this is nothing but magnetic circuit. So magnetic circuit is very important in our life and applications. The magnetic circuits care about the winding of wires either on air or across a material called ferromagnetic material. It's based on iron or made of iron with many kind of iron, and we are going to discuss some of these materials. Right. Let's start with the permanent magnet. You know the permanent magnet is a natural material existing in our earth, and there is internal forces in these magnets can flow the magnetic flux between poles N and S. All of time, flux lines are moving from pole N to pole S. If we have two magnets, like in the middle figure here, and these magnets are free to move, you can see that the flux lines are moving from N to S, and in few seconds, the flux lines will make its path very short in order to decrease the path up till zero, which means there will be an attraction between the two poles. This is if the poles are different, N and S. So the characteristic of the magnetic field lines itself, it's work all of time to decrease its length, okay, and try to move in straight lines. Try to move in straight lines. Yani, if we have larger magnets, you will find all of lines are moving in straight. Only the lines at the ends or edges can only have some curves or يعني different angle of motion because of something called the fringing. Okay, this is normal. However, the majority will move in straight lines between N and S. So these are the characteristics of the flux line itself. Like, what is the difference between permanent magnets and electric magnets? electric magnets can make the same function of permanent magnet. However, if the electrical supply is connected, if the electrical supply is disconnected from the electric magnets, it will not act as magnet anymore. It will be just a piece of material, a piece of iron or a piece of metal. Okay, شباب? So this is the difference between electrical magnet and permanent magnet. Type, which type is used in our motor? Actually, we used both permanent magnets and electrical magnets. However, electrical magnets magnets are used too much compared to permanent magnets in all of our today life applications. So let's start make some definitions for the parameters of magnetic circuit, and we are going to describe in more details. If you have some flux lines moving in a circular area like that, these flux lines has magnetic flux density B and also has magnetic flux intensity. Intensity, it means the intensity of the flux lines itself. However, density means the amount of flux lines divided by the cross-section area that's going to be crossed. So if we have flux lines phi, which is called the flux and measured in Weber, and we have a magnetic material that's going to be used to flow this flux or to collect the flux, this material has cross-section A, we will have magnetic flux density equal to B, where B equal to phi divided A. The flux intensity itself, it's equal to ampere turn per meter. It depends on the supply, which is ampere turn. So the supply of the magnetic circuit will be called ampere turn. We have another term which is lambda. Lambda is the flux linkage. Flux linkage. So there is classification for flux. There is flux linkage, which is useful to our device, which means the amount of flux that's going to link between the two magnets. And we have also flux leakage, which is going to be in air and out of the magnets, and this is considered as losses in our magnetic circuit. So we will care about the lambda, which is the flux linkage. Also, all of magnetic circuits are used to make inductance. No inductance without magnetic circuit. So what is the inductance as a function of the parameters we are going to describe as well. And I is the electrical current that is going to supply the electric circuit. We have some relations. B, which is the flux density, equal to mu multiplied by H. H, as we agreed here, is the flux intensity, and the mu, it's called permeability, and we are going to describe it in detail. And B equal to flux divided A, phi divided A, where phi is the magnetic flux and A is the cross-section area of the magnetic material. So now we agreed that we have source for the magnetic flux. This source is called MMF, magnetomotive force, and equals to N multiplied by I. And we have general relation. It's very important in solving problems we are going to use, which is Ni equal to HL equal to phi multiplied by reluctance. Also, we are going to define the term reluctance. So these are the main definitions we are going to use in our chapter. Starting from the beginning, what is the magnetic field intensity and what is the role of moving this flux intensity or field intensity in a magnetic material, and what is the relation? We are going to describe all of this. If we have a conductor carrying a current like that, as you can see, if there is current moving in this conductor, a flux will be start rotating around this conductor. So what is the role of the or the direction of the flux? Using right hand, if the thumb in the direction of current, the other fingers will refer to the direction of magnetic field or H. تمام يا شباب؟ So in the in the figure here, in the left hand side, as you can see, the current is moving to up, and there is a circle around the hand. As you can see, from our side, the flux is moving toward to the right side, and from behind the hand, the flux is moving on the left hand side. So this is according to what's called right hand rule of Maxwell. So this is called Maxwell right hand thumb rule. Here in the right hand side, you will find the opposite. If the current is in the reverse direction, the current is moving down, so the flux will move in the direction of the other fingers, as you can see. Right. If we have many currents due to many conductors, so we will take the summation of currents in a certain direction. So if we assume the current I1 is the positive direction, as you can see, I2 is in the same direction, so I1 will be summated to I2, and I3 will be in the opposite direction. تمام؟ طيب, if we are if we connect this wire across across a material like that, for instance, this is toroid, and you can see here we have many turns of coil, so we have n turns. Okay, so the sum of current here will be n multiplied by I, because we have n turns and the current are in phase for all of turns, so Ni. What is the relation between current and flux density? This is, flux intensity. This is what's called Ampere's circuit law. In Ampere's circuit law, it's stated here that the surface integral of HDL, equal to the summation of currents. Now, assume that we have different directions of currents like that. So the current will be I1 here plus I2 minus I3, because I3 in the opposite direction. And H will represent the vector of flux intensity. And if it is moving in tangent to the toroid, like that here, tangent, so it means it's going to be moving in that direction inside the material itself. So there will not be any angle theta. The theta will be 0. However, if there is deviation with angle theta due to what's called the fringing at the ends or edges of magnets, so we will have another component of flux. So we will consider only the angle of cosine theta. Type. So if for the previous example of toroid, assume this is the average length of the toroid itself with the circle R, as you can see. Let's return back again. This circle has radius R, okay, which represents the average length of the flux moving in the magnetic material, okay, and H represents the tangent of this circle, which at this point, exactly at this point, and the unit of length is dl. So the relation HDL cosine theta, integration of HDL cosine theta equal to summation of I. If we apply this for one turn of coil, so we have only one turn, so N multiplied by I equal I only. So the relation will be HDL, integration of HDL equal I, and DL, the integration of DL for one circle, which is the average length that the flux intensity is going to travel. So it will be 2 by R. So H multiplied by 2 by R equal I, and this is the relation of the H, which is the magnetic flux intensity. So this is the magnetic flux intensity due to one turn of coil. If we have N turns, so it will be Ni. Another term, which is magnetic flux density, and we agreed together flux density B equal to the flux lines phi divided by the cross-section area of the magnetic material. What is the relation between B and H? Actually, this relation depends on the material itself, because it will represent after that the resistance of the material to the magnetic field moving. The resistance of the material, we will call it as reluctance. We will describe it later. So what is the relation that we can say this material is good enough to be used in magnetic circuit for electrical machines, for any application? So we have to define this term, which is mu. Mu is the permeability of the material, and this variable, mu, is a function of two variables. First is mu naught, which means absolute permeability, and this absolute permeability is the permeability of free space for air. So if the medium of transferring the flux is air, mu will equal to mu naught, and the value of mu naught is 4 pi multiplied by 10 to power minus 7. So this is the value of absolute permeability. Now, according to any kind of material, each kind of material has its own mu r, or relative permeability. How we can, or what is the value of this relative permeability? طبعا for free space or air, the relative permeability will be 1. However, for any kind of material, it will be high value. For instance, شباب, for free space, for free space or electrical conductors, yes, electrical conductor made of aluminum or copper are similar or very close to free space because it's not magnetic material. Aluminum or copper are not considered as magnetic materials. However, ferromagnetic materials like iron, like cobalt, like nickel, all of these materials have high permeability. For instance, mu r used in electrical machines needs a magnetic material of range 2000 to 6000. What is the meaning of having high value of permeability? This is described here. A large value of permeability implies that small currents can produce a large flux density in the machine. So this is very important. If your material has high value of relative permeability, this means that you can have high flux due to small currents. For instance, these are some curves for some ferromagnetic materials. We have here cast iron, we have cast steel, we have silicon steel. All of these are ferromagnetic materials. And the slope of these lines, nonlinear curves, will be the value of permeability, mu. As you can see, because these are nonlinear lines, so the value of permeability will not be constant for the machine. It's different according to the amount of current which is coming from the conductor, which is represented by H here, which is flux intensity. So according to the flux intensity, it can produce certain amount of flux. Like if we compare the three materials, for instance, at 200 ampere turn per meter, يعني at this value, which material can produce higher magnetic flux? Magnetic flux density. Hi, Shabab, it's a question for you. Which material of the three materials can produce higher flux density at 200 ampere hour per turn?
Silicon?
Yes, silicon steel. So we will prefer silicon and be sure it's silicon sheet steel. It's not one complete core, silicon sheets. So it's silicon sheets, which means we can make the material as slices and collect these slices together to make one core. So sheet steel is very good. Silicon sheet steel is very good for electrical machines, as you can see, because at low value of current or low value of H, both of them are related to each other because H depends on the current as we described. So low value of H or current can produce high value of magnetic flux density. Right. So this is the regarding the permeability of material. So we prefer the material that has high permeability. Let's have an example for toroid core in order to drive the relation for flux density. So if we have toroid core like that, with cross-section area A, circular like what that you can see, and here the average length can be calculated as the circle by 2 pi r, which is the perimeter of the circle of radius r. So this represents the average length for the flux lines moving here inside the core. And this coil has n number of turns. So simply apply Ampere's circuit law. So HDL, integration of HDL equal to n multiplied by I. Why n multiplied by I? Because we have many turns and all of turns will have the same direction of current. تمام يا شباب؟ So we can say HL equal NI and L equal to the perimeter of the circle, which is 2 pi R. So this is the relation of H now. We have to note that the source of magnetic is the MMF, which is the source of current here. So we can call MMF as the multiplication of NI, which is equal to HL. So this is considered as the source of flux in our circuit. If you would like to calculate H, so H will equal to NI divided L. Based on that, we need to calculate the flux density B. So we can say B equal to mu multiplied by H. So it's mu multiplied by H, which is NI divided L. And B is measured in Tesla, as we agreed before, or we can measure it in Weber per meter square.
Which mu?
Sorry?
Which mu is this?
We said mu is the permeability equal to the multiplication of relative and absolute permeabilities. And if we return to previous slides, here mu is the multiplication of mu r and mu naught.
Okay.
Okay. But what is the amount of flux? The overall value of flux. Flux can be the summation, the multiplication of B with area, or the relation based on a small part of area, it's integration of B dA. Okay, and if you integrate the dA according to the cross section of the material to get the cross section A, so the flux will be B multiplied by A, which is measured in Weber. Will be the average flux density, as we stated before, and A is the cross-section area of the toroid here. We agreed here the toroid area is the area of circle. Okay, شباب? We may have different configuration of cores. We may have square cross-section, not circular cross-section. It's up to the core type. If we need to calculate the value of flux as a function of B, in the relation we obtained from the previous slide, so phi equal to B multiplied by A. So we can say phi equal to mu Ni divided L, which is the value of B, multiplied by the cross-section area A. If you move mu and A on the denominator, so the relation will be Ni divided L divide mu A. L divide mu A will represent the resistance of the magnetic core itself, which is called the reluctance. It's called reluctance. تمام يا شباب؟ So the reluctance represent the limitation of flux in the magnetic material. Okay, and the relation is L divide mu area. So reluctance is function of the average length of the material, cross-section area of the material, and the permeability of the material. So it's mainly depend on the material of the magnetic core. We can refer to the 1 divided P, so reluctance equal 1 divided P, where P is the permeance of the magnetic path. However, the word reluctance or term reluctance is the mostly used in our life. So if now we would like to make a comparison between electrical circuit and magnetic circuit, simply we can say that the flux which is set up in the magnetic core is equivalent to the current which is moving on the wires. So these are according to each other. This is the flux which is going to be set up flux in the magnetic core, and the current which is going to flow on the electric circuits. The source depends here on F, which is MMF or magnetomotive force, and the source in electricity is the EMF, electromotive force, which is the supply voltage. The limitation on the magnetic serial for the flux is the reluctance, and the limitation of the electric current in electric circuit is the resistance. So simply these are the parameters, and this is a comparison. So driving force, which is the supply, in electric circuit it's EMF, in magnetic circuit it's MMF. طبعا يعني take care, electric circuit is here, magnetic circuit is here, not left and right. يعني I take the table and figure as it is from the reference, but in order to make it not confusing, this is the magnetic material and this is the electric circuit. Okay. Fine. So again, the forces EMF in electricity or electrical circuit, MMF in magnetic circuit. The source produces current in electric circuit and the flux in magnetic circuit. The limitation of the material itself against current or flux. In electric circuit, the limitation is called the resistance, and the corresponding in magnetic circuit is called reluctance. Right? And the relation reluctance equal to L divided by mu A. Take care, A here, small a, this letter is referred to the footnote. It's not to power a small a. Huh? Okay, this is just to refer to this comment here. Okay, so this is the comparison between the two circuits. Type. In magnetization curves of electrical systems, for any kind of machine, شباب, we will have something called magnetization curve. This is nothing but the relation between B and H, which will be reflected as a relation between V and I, or EMF and I, in any magnetic core or in machines or transformers. So, as we described, we have this pH curve, and the relation between B and H is the permeability. Here the permeability is small, okay, because of the slope of curve, and here it's called saturation, and here it's very high. So which place is better to operate, at high or a small permeability? ها شباب. It's a question for you, Shabab.
High.
Which is better?
I think high is better.
Hmm.
Low is better.
Right.
What is the
Actually, if we reach to the saturation and work with values in high reluctance, we faced a lot of problems in the machines because of something called harmonics. It's make a lot of harmonics in machines if we work in very high value of the reluctance after the saturation curve. So, يعني the best value to operate any magnetic circuit or any electrical machine is at the knee of the curve. So this is the best place to operate the machine. So the value of H will not be very high like in saturation. So you will not have a lot of current consumed. So it's going to save power. And also here the value of B is high. تمام? If you work in the small value here, you may not have the sufficient flux to operate your loads. Okay? However, it's not logic at all to move to saturation and high. Why? As you can see, from saturation here, the value of B is almost constant. Is it right? Or the increases in B is very small. However, you pay much current. Is it right? صح يا شباب؟ يعني I don't like to confuse you, but you have to recognize the difference between we should select material of high permeability. However, it's not correct to work at the value of high permeability of the core itself. Again, and it's two different things. When you select magnetic material, it's better to select the magnetic material of high permeability, like what we already compared in the previous slides here. Okay, which one is better? We said the silicon sheet steel is better because at small value of H, it can give high value for B. This is as a comparison between the three cores. However, for the silicon sheet steel itself, is it better to work in this region or in this region? In this region here, we are going to pay less current and get high value of flux. However, here, if we reach to, for instance, to 1000 ampere turn per meter, we will pay a lot of current. However, the increase in B will not be very high. And also in this region, you will have a lot of harmonics in electrical machines. So it's not preferred to work at the high values of permeability of the material itself, which means close to the saturation region. Okay. However, when you design any kind of machine, it's better to select the material which has high permeability compared to other materials. يعني is it clear يا شباب for you؟
دكتور دكتور سؤال.
الصوت مش واضح معلش.
Can you hear me now?
Yes, تفضل.
What do you mean by paying high current?
Paying high current, it means you supply more current to get flux. يعني we agree together that H equal to N multiplied by I, or HL equal to N multiplied by I. L will be the function of the magnetic length itself. So assume this value is constant. So we can change current in order to change H. Okay? Is it right? Because in the relation, here we agreed together that HL equal NI, which is the MMF required. N will depend on the number of turns, and we are going to assume this is fixed for a magnetic circuit. And if we have ready magnetic circuit and this circuit is working and designed already, so we cannot change N anymore. For instance, like motors. Motor, in order to have better performance, you shouldn't make a new machine or rewind the machine again. You have already the machine, but you need to operate the machine at the best condition. Okay? So N, we can assume it as constant. L also constant because it depends on the design of the core itself. And we are not going to change the core of the machine in order to have better performance. However, we can change the amount of current absorbed by the machine in order to get different values of H. Okay? If we return back to the curve again, here we will supply the core with small current at 200. However, for sure, at 1000, we have to supply the core with high currents. Is it right? Right. If we compare, if we change the current from the H value of 200 to 300, can you see the difference in B? It's changed from 1 Tesla to 1.1 Tesla. Okay? So here, paying more current is useful because you get higher B. However, if you can see here, from 800 to 1000, we increased a lot of currents, okay? However, the change in B is very small. So this is not good. It's not good to operate at that region. So it's better to return and operate at the region behind the knee curve, behind this part. So try to work at that part, linear, and after the linear by small portion, in order to avoid the saturation and paying a lot of money in terms of energy consumed, in terms of current, okay? And you will not get much more flux from the circuit. تمام؟ Is it clear now? باشمهندس كان بيسأل.
Yes.
Okay. So, regarding this curve, شباب, we prefer to operate any kind of machine before saturation, because at saturation you will not get much more flux, you will pay a lot of current, you will have some losses in the machine in terms of core losses, and we are going to describe this in details, inshallah, by the end of this chapter. I believe the time is due now.
دكتور the attendance.
I will take the attendance now.